Welcome back to the Chapter 6.2 notes. This is applications of radian measures. And as I watched through some of these videos, I realized that it's a little difficult to see some of what's going on when this is the vertical. So we're going to switch to horizontal, see if we can make this type a little larger and easier to see. So last example, dealing with arc length and area of a sector. Example 4. Says we have a pendulum of a grandfather clock that's 3 feet long. It swings back and forth, creating a 45-degree angle. We want the length of the arc created by the pendulum after one swing. So we are looking for arc length. We are going to use this formula, r theta. We know what our radius is. It's 3. That is the length of the pendulum. Now, theta, I can't put degrees in. 3 times 45 degrees gives me 135 degrees, and that is definitely not the distance along the arc. So our theta, to start, has to be converted from degrees to radians. So going back to the last set of notes, we are multiplying our 45 degrees by pi over 180. 45 does go into 180 4 times, so this becomes pi over 4. So we got 3 times pi over 4. R times theta. I got 3 pi over 4. Again, our radians are kind of unitless units, dimensionless units. And since the pendulum is 3 feet long, the length along the arc is in feet. Now, if somebody were to ask me how far this pendulum swings, I would definitely not use 3 pi over 4. That is not going to make sense to a whole lot of people. So I am going to go ahead and multiply this out. Notice the squiggles, because I do end up rounding to 2 places, so this is an approximate, but approximately 2.36 feet is the length of the arc created by the pendulum after one swing. Okay. Next thing we're going to move on to, and we have got formulas for the bottom of this page. The examples are on the next page, so we're going to kind of dump this all in together. Linear velocity. So let's talk really quick about the difference between speed and velocity. Speed is always positive. It's how fast we're going. Just how fast. Velocity, though, is speed with direction. So a positive velocity means we're going forward, we're going up, whichever way you decide the positive direction is. Negative velocity means we are going backwards or the opposite direction. Okay? So whereas speed is always positive, velocity can be either positive or negative. We have some formulas here. We have our linear velocity. The velocity is the v. Our linear velocity formula is s over t. V is linear velocity, s is the arc length, t is the time. So basically we're finding how fast we're going around that circle by taking how much of the circle we're covering and dividing it by how much time it took us. Makes sense. We also have angular velocity. Angular velocity means, and a lot of times it's easier to find the angular velocity first. We use the symbol that looks like a super fancy W. It's actually a lowercase omega, the Greek letter omega. So the capital is right here. Lowercase looks like a W. We use that omega for angular velocity. To find angular velocity, we're taking the central angle that we're sweeping out and dividing by the amount of time it takes us to sweep those out. Okay. Units of angular velocity are radians per second. But again, radians is dimensionless. It does not necessarily give us a way to talk about what we're measuring. Okay. We can plug and chug and substitute. Our linear velocity is our radius times our angular velocity. So there is a relationship between the two, of course. Okay. And then we also have all of the formulas down here. So here's our arc length, S equals our theta. Here's our angular velocity, omega equals theta divided by t, and our linear velocity. Velocity is speed divided by time. Okay. So let's put that together and work through a couple of examples here. We have the blades of a wind turbine that are 116 feet long. Propellers rotate at 15 revolutions per minute. I apologize, the A and the B is on the next page, so we are just going to split pages here. Okay. A wants the angular speed of the propeller in radians per minute. So let's talk about what we've got up here. We've got 15 revolutions per minute. A revolution is going to be once around the circle. That's what a revolution means. So A, if we want that angular speed of the propeller in radians per minute, I am going to make sure that I am conscious of including the units. A lot of times, using the units tells me what I need to multiply or divide. So we're trying to find angular velocity. It says angular speed, so if we end up with a negative, we'll just make it positive. But our angular velocity here, we're taking my 15 revolutions per minute. That's how fast that propeller's rotating at. That's what it tells me up above. Let's okay. And you know what? Because I don't like thinking too hard all the time, I know I want an answer in radians per minute. I already have minutes in the denominator, so I need to convert from revolutions to radians. So 1 revolution, I said, was once around the circle. That is 2 pi radians. Revolutions and revolutions cancel. I multiply straight across. I get 30 pi radians per minute. Let me slide that in here so it looks a little more cohesive. Radians per minute, 30 pi radians every 1 minute. Could write 30 pi over 1. Don't necessarily need to do that. Okay. B wants us to find the linear speed in feet per second of the tips of the blades. So our linear speed is our V, and since I already have angular velocity, I am going to go back up here and I am going to use this formula right here. My linear speed is the radius times the angular velocity. We know our radius from up above is 116 feet. We know our angular velocity, what we just found, is 30 pi radians per minute. Again, radians is already unitless. So if we ignore this, I have feet over minute, 116 times 30 pi feet per minute. So we're going to go ahead and multiply that. I get 3,480 pi. Feet per minute. And when I multiply that out, I get 10,932.7 feet per minute. Okay. Number 6, a car is moving at a rate of 28 miles per hour. The diameter of its wheels is about 2 1/3 feet. Find the number of revolutions per minute the wheels are rotating. So first thing I notice is that the rate the car is moving is 28 miles per hour, but I want my answer in minutes. Okay. Also that my diameter is 2 1/3 feet. So whether I keep everything in feet per minute or inches per minute, we're going to figure out as we go through. Okay. I will be honest. I'm going to go to B and I'm going to take a look at finding the angular speed first. Scratch that, I lied. We're going to use revolutions per minute to find the angular speed. So no, we're doing this the way that it's written. So first off, we know that this car is traveling at 28 miles per hour. I know that I want my answer in minutes. So the first thing I'm going to do is convert from hours to minutes. So I'm going to multiply by 1 hour over 60 minutes so I can cancel those hours. Second thing I realize is that this is in miles per hour, but the diameter of the wheel is 2 1/3 feet. So I got to change from miles to feet at a minimum. So I need to cancel miles, so my miles goes down here. I got 5,280 feet up here. Miles and miles cancel. Now let's talk about how we want to take care of this circumference, 2 1/3 feet. 12 inches per foot. So the 2 feet, 12 plus 12, 24 inches, another third of a foot, another 4 inches. That's 28 inches. And because I don't have any specifics about whether I want this in inches or feet, I am kind of inclined to do this in terms of inches. Even though it's got feet. Okay. So I think I just said I was going to convert to inches. I don't think I'm going to do that. Our circumference is pi times diameter. Our diameter is 2 1/3 feet, so we're going to go with 7/3 pi feet. Let's do that. Times. Because I'm now realizing that changing it to inches, 7/3 pi feet. Our feet cancel. We have revolutions in the numerator. We have minutes in the denominator. So now we just have to crank through the numbers. Okay. We have 28 times 5,280 in the numerator. That gives me 147,840 revolutions over, I got 60 times 7/3 to multiply in the denominator, and I'm going to do that right here. 60 times 7 pi over 3. We can cancel a 3 in both. We've got 20 times 7 pi, so 140 pi. And I am going to go ahead and convert that to a decimal so that we're dividing decimals by decimals. I mean, let's be real. So we have where am I? 140 pi, and I wrote that down. We get 439.822978230 minutes. We are going to divide that, our 147,840. We're going to divide by our 439.823, and we get 336.14 revolutions per minute. Poor planning, poor planning. Let me move this for a second and I'm going to rewrite it. Okay, so our circumference was pi times the diameter. They gave me pi times my 7/3 feet, which is 7 pi over 3 feet. That's where we got that circumference. Now, I will be honest with you, last time I did this, and I was just referring to my notes, which was my little bit of momentary confusion, I did convert to inches, and I ran everything with inches. We got the same number of revolutions, 336.14. So if you are more comfortable working with whole numbers and you wanted to convert that to 28 inches, 28 pi inches for a circumference, that would be fine too. We're going to get the same number of revolutions, okay? So now we want the angular speed, and we go back up here. Our angular speed is angles divided by time. So our angular speed, we want an answer in radians per minute. So this is one of those cases I am not going to worry about formulas. I know that I have 336.14 revolutions per minute. I know I want angular speed in radians per minute, and I know it's 2 pi radians for every revolution. So I'm going to go ahead and cancel, multiply everything out. I get 2,112.03 radians per minute. Again, comfort with that proportional reasoning is going to help. 18, we have the edge of, 7, we have the edge of a Ferris wheel turning at an angular velocity of 12.5 radians per minute. What's the angular velocity at a point 10 feet from the center? So let's think here, angular velocity. Angular velocity does not change with the radius. It's how much of the angle is being cut out over time. So angular velocity does not depend on the length of the radius. So the angular velocity is the same for any distance from the center. That means our angular velocity here is 12.5 radians per minute. Woohoo! Now our very last example here, 8, we got a truck with a 28-inch diameter wheel. Weird, same as the diameter above. Traveling 55 miles per hour, find the angular velocity of the wheel in radians per second. Radians per second. So again, I am going to start with my 55 miles per hour. Keep in mind that what I'm trying to get at is radians per second. So the first thing I'm going to do is convert my hours to minutes and my minutes to seconds. Hour, minute. I now have miles per second. Okay. I also know that because my circumference is going to be in inches, circumference is pi times the diameter, 28 pi inches. I need to convert from miles to inches. So I have miles in the numerator. My 1 mile goes in the denominator, 5,280 feet. So miles cancel. And then 1 foot in the denominator, so I can cancel those. 12 inches in the numerator, feet cancel. Right now I have inches in the numerator and seconds in the denominator. And I want angular velocity in radians per second. So now I got to take a look at how to get rid of inches and put this in terms of radians. And I have that right here over on the right-hand side. My circumference, 28 pi inches, that is all the way around. So 28 pi inches is the same here as 2 pi radians. So here's my last conversion. I got 28 pi inches, 2 pi radian. My inches cancel. I can also cancel this pi here just to make life easy, and I could cancel other things, but in the interest of time, we are going to multiply across the numerator. I got 58 times 5,280 times 12 times 2. My label up here is radians. In the denominator, I have 60 times 60 times 28, and then seconds. Now, last time I multiplied everything in the numerator and multiplied everything in denominator and divided. I want to point out that I can set this up a different way. Everything in the numerator is getting multiplied, yes, but everything in the denominator is getting divided. So I can just go 55 times 5280 times 12 times 2 divided by 60 divided by 60 divided by 28. And I bring this up because a lot of people will multiply the numerator, 55 times 5280 times 12 times 2, and then divide by 60, but in their mind, 60 times 60 times 28, once you hit that division, you're telling the calculator to divide everything after, and you're not. Dividing and multiplying are the same. So we are going to go ahead and crank this out. If you want to double check my math, you can go ahead and multiply that whole numerator, multiply that whole denominator, and divide that way. And compare, make sure you get the same thing. I do this and I get 62.86. What do we have? Radians per second. There's our angular velocity. Okay. Now, we're asked for one more thing. How many revolutions are made in a minute? So I've got 62.86 radians per second. I want revolutions per minute, so I got 60 seconds over 1 minute. Seconds cancel. I now have radians per minute. I want revolutions. I know 1 revolution is 2 pi radians. And so now, same situation. I got 62.86 times 60. I'm going to divide by 2, divide by pi. Even if 2 pi is written together, there's that magical invisible multiplication between them. We get 600.2687, so 0.27 revolutions per minute. And let's see if I can color code our answers here. And a lot of this can be figured out just by taking a look at the units they want on the answer. And that's it for 6.2.